N inner product X will equals to C2. Okay, so for all point, let's say A1, if we plug into the hyperplane here, which we will get an inner product A1, and that will be smaller than C1. And if we have another point, let's say that B1 here, inner product B1, then that will greater than C2. Okay, so that's what this claim is talking about. And the proof, okay, the proof we will show only one side, and then the same argument will apply to another side. Okay. Okay, so how to prove it? So suppose we have a point, A plant, that is in A, and when we plug into the hyperplane LA here, we find that it actually is greater than C1. That means it will fall on the right side of this plane, right? So graphically, it looks like this one. Okay, and since that the set A is actually a convex set, that means all the point on the segment from A0 to A plant also belongs to the set A as well. So we can actually find one point, we call it A double plant, that is going to have the you can draw a right triangle here, okay? And once we draw a right triangle here, we immediately know that. Okay, so let's call this one D star, which is the minimal distance we have shown, and this is D1, and we immediately know that D star is larger than D1 by this graph, right? And that means the original point A0 is not, the distance, this distance is not the minimum distance over A and B, which is contradict to our claim 1. So that means these things couldn't happen. And that's how we prove this claim. Okay, so that is the logic behind it. And when you put it in the word, then it looks like this one. And that's how we prove the separating hyperplane theorem. Okay. Okay, so if you look closely to this proof, then actually it uses all three conditions: non-empty, disjoint, and convex. Okay, so that's why this theorem is powerful. So once I told you that these two set has these following conditions, then I can immediately tell you there always is a separating hyperplane. Okay. Any questions? And then we are going to move on to the matrix. Okay, I seldom put the abstract here, but I have to mention it because this guy is my hero. So you can search on the YouTube, like Gilbert Strand's linear algebra, and like he's a genius. Although like he talk really slow, so you can speed up a little bit that to prevent you from sleeping. But he's a genius. So if you want to have a further, like deeper understanding on linear algebra, I really recommend you to watch his lectures. Okay, and that's it. Right, matrix. So this is the first definitions of today, linear transformations. So let's say that we have like these two vector space V and W, and there's a functions that will translate V to W, which is called linear transformations. If like for all vectors in V and like C in a field that satisfy these two property. Okay. Right. Okay. Questions. Is linear combinations linear transformations? If you think is yes, please raise your hand. If no, raise your hand. If you don't know what I'm talking about, raise your hand. Okay, let me repeat once again. So, this is the definition of linear transformation, right? So for any vectors in big V, like in the vector space V, it has to satisfy these two properties, meaning that, okay, if you operate the sum of these two vectors, you can actually operate respectively and then add them out. Or if you have a vector that ties some like real number C here, you can actually take C out of the operation T and then multiply it later. Okay. And what is the definitions of linear combinations? Okay, so this is the linear combination. So it says that we have a bunch of vectors, v1 to vn here, and we also have a collections of real numbers from a1 to an here. So linear combination is like you times each constant number or real numbers in front of the vectors, and then you add them up. So this is linear combinations. Okay, and does that fit into that definitions? Let's say that we have another vectors, call it x, x1, x2, xn, for another vectors. Now, when we want to do the linear combinations with the same real numbers a there, how should we process? So it's more like a1 times v1 plus x1. Okay, then A2 V2 plus X2 this is Vn plus Xn. Okay, so this is a linear combinations of these two. Like once first we sum up these two vectors one by one, and then we multiply by the real number over there. And this obviously it can be written as A1 times B1, A2 times B2, Bn, and okay, A2, X2, and Xn. Okay, so I should define an operator first. So operator T of the set V is A1 plus V1, A2, V2, and Vn. So this is the linear combinations operator. So we can write it as plus. Okay, so it satisfies the first property, right? Just like multiplication, and you separate it and like rearrange